Welcome to this week 5 recap video for 4310. So we're just going to focus mainly on supremum, infimum, and lim sup and lim inf. So the previous week we did more Cauchy sequences and monotone sequences. This is really setting us up to actually get the tools we need to prove that Cauchy sequences converge. So let's just go ahead and get started. The definition I'm starting with is 4.2 from the book, and this is about a set being bounded above or bounded below. And they're pretty straightforward. You're basically saying a set's bounded above, like a set capital S, if there is actually some number m such that it's an upper bound for the set, meaning that for all the terms, the little s and s, that s is less than or equal to m. And there's something similar for being bounded below, where a little m is a number that bounds everything from below, of course. And then there's, a set is bounded if it is both bounded above and below. Then we moved on to saying, well, what does it mean to be a good bound, perhaps? Because we talked about like the interval 0, 1, said, well, there's all sorts of upper bounds for that. There's like 1,000, 100, 1.2, all of these are upper bounds. But maybe is there a best upper bound? And you could think of it as like, if I have an interval like 0, 1, choosing a number way out here is an upper bound, choosing a number way out here is an upper bound. But I kind of want to choose the smallest of all these numbers so that I get kind of the tightest upper bound I can. And I want, in a sense, then the least of all the upper bounds. And similarly, for something bounded below, I want the greatest of all the lower bounds. And so then this motivated the definition of the supremum and the infimum of a set, supremum being the least upper bound, and an infimum being the greatest lower bound. So they're like, on an interval, or you're basically saying the infimum is like, I'm taking lower bounds, which are the numbers below that open parenthesis, and I'm kind of picking the largest of all of them, which happens to be actually this number, even though it doesn't belong to the set. Similarly, for supremum, I'm saying all these numbers are upper bounds, and I'm going to move all the way to the left and take the least of them and create kind of this tight grip of bounds around all the terms in the set. And let's see, so we move forward and we ask a question like, well, do these supremums and infimums, being maybe the best of the bounds that we could find above and below for a set, do they always exist? Well, in fact, the completeness axiom tells us that if you have a non-empty subset that's bounded above, then in fact there is a least upper bound. It's something we can't prove, but then we can prove a corollary to it, which reveals a useful relationship between the infimum and supremum. And that is that if a set is bounded below, it has a greatest lower bound. And in proving that, we establish really this relationship that's stated in this theorem, that the infimum is equal to the negative of the sup of the negative of the set. So we went through this. The argument for proving this was actually, in some sense, pretty straightforward. We just take points from the set and we bound them below by something. There is a lower bound. And then by taking the negative of the terms in that, then we actually find that this negative m serves as an upper bound for the set negative s, which is then a set that's obviously then bounded above. And so the completeness axiom can be applied to it to say, well, then there's some supremum, and then you just play with negatives again, and you multiply an inequality by -1 to switch the direction, and you get the infimum is equal to the negative supremum of the negative set. And then we just said, well, we can also do this when the symbols happen to be infinite. And finally, we proved some useful results about the infimum being less than or equal to the supremum, and that if they're the same thing, then the set has to be a singleton set, right? And we talked about two different proofs for that. I give one here on the screen, and you can just pause the video and look at it if you need to. But that's actually really useful, because this then, as we move towards lim inf and lim sup and relate them to the inf and supremum of subsequential limits, we start to see how we can prove a Cauchy sequence converges. The final real useful result from infs and sups that we covered in class, there's other useful ones in the homework, was that if you had non-empty and bounded subsets, that if you took S to be a subset of T, then you had this relationship. The inf of T is less than or equal to the inf of S, which is less than or equal to the sup of S, which is less than or equal to the sup of T. And this is actually a really, really nice result, because what it's saying is that if you take a subset of a set, then the only thing that could have happened to the infimum is it could have been made larger. than the infimum of the original set. And the only thing that could have happened to the supremum was it could have been made smaller. And that makes sense because you're taking a subset, which means you're potentially throwing away, or removing terms that are maybe large or small that were kind of propping up the sup and the inf. And so it's a very intuitive result if you take a second and think about the grammar of the words, like what is a greatest lower bound, what is a least upper bound, and what does it mean if I remove elements from a set? I can only possibly make things, larger, or in terms of lower bounds, or smaller in terms of upper bounds, because maybe I got rid of large or small terms in the set. So we went through that, and then we this was a useful result. The sup was equal to of a union is equal to the max. The way we went through that was we just said, okay, I'm going to take an element from the set, and then I'm going to establish that the max of the sup of S and the sup of T is an upper bound for the union, and that means the supremum of the union, which is the least of all upper bounds, has to be less than or equal to that. And then we just work with proving the additional inequality. So again, we went through this in class. It's on the screen, and you can pause this video to look at it if you like. Okay. So we then discussed lim sup and lim inf. I'm not going to go into great detail because we spent a lot of time in class on it. I really like these definitions right here more so than these other equivalent definitions. And we related this to, plots of sequences in class. The main thing to realize when you go through kind of the sequence of results we ultimately go through is, in some sense, the following. That if you take the set of all subsequential limits of a set, then the supremum of that set is the lim sup, and the infimum of that set is the lim inf. And so now you see that if the sup is equal to the infimum, meaning that the lim sup is equal to the lim inf, then in fact there's only one subsequential limit, and that has to be the limit of the sequence. So that's one way to prove that a sequence converges, is you prove the lim sup is equal to the lim inf. And then this is effectively what's done in the proof of this theorem right here in the book. When you read the proof, a sequence is convergent if and only if it is a Cauchy sequence. And what you do is you say, I'll take a Cauchy sequence and I'll show that the lim sup is equal to the lim inf. So that's, when you read the proof, that's exactly what's going on. And so it's fundamentally just using this result. I'm going to scroll back up to it. Where is it? Here, right here. That if the inf is equal to the sup, then the set S is a singleton set. That's kind of all that's going on to prove a Cauchy sequence converges. Now, it looks more complicated because it's involving these lim sups and lim infs, and these seem like complicated objects, but they're not that bad. We were plotting them. You can get a sense graphically of how these things work. But I just want to just give you again this overview of we established these bounds and these relationships between sups and infs, and it was really so that we could get that Cauchy sequences converge. And that was based upon applying this theorem right here, that if the lim sup and the lim inf are the same thing, then that set S can only have one element, and then that is the limit of the set. That is how it all ties together from chapter 1 to chapter 2, basically from section 4 all the way out to section 11 in the book. So I just want to conclude there. That's kind of a very big picture recap of the week. I'm admitting a lot of complicating details that we went through, but maybe they're not so complicating, but they're worth spending time with nonetheless. So next week, after this oral exam week, we'll definitely be doing a lot of these activities and examples. So thanks for listening, and we'll see you in class.